Welcome to variation of parameters for nth order ODEs. So the general idea, let's consider an equation of the form P0 of x times the nth derivative of y plus P1 of x times the n minus first derivative of y plus all the way down to Pn of x times y, all set equal to f of x. With corresponding homogeneous general solution. Y equals C1, Y1 plus all the way up through plus Cn, Yn. Just like with second order, the way we will run variation of parameters is we will replace those unknown constants with unknown functions of x. So to run variation of parameters, we'll assume that y is equal to u1, y1 plus all the way up through un, yn, where the use of I are functions of x. Then essentially our goal is to solve for the ui. If we know those functions, then we have our solution. So our goal is to solve for the ui. So in this case, note, we have n unknowns. We have n unknown functions. So if we are trying to solve for n unknowns, we can have n equations. We can have a system of n equations. One equation will be our differential equation. With y equals u1, y1 plus all the way up through un, yn plugged in. So this will be one equation. We get to pick the remaining n minus 1 equations. So what we are going to pick will be the equations u1 prime times the kth derivative of u1 plus all the way up through un prime times the kth derivative of un set equal to 0 for 0 less than or equal to k less than or equal to n minus 2. So going from 0 to n minus 2, that will hit n minus 1 equations, what we wanted. we can then sort of use this to find the derivatives of y. So what does this mean? For the derivatives of y, so y itself will just be u1, y1 plus all the way up through un, yn. Y prime, we would have u1 prime, y1 plus u1, y1 prime plus all the way up through un prime, yn plus un, yn prime. Now, all of those terms with the ui prime, those all add up to 0 by our first equation. So this is just equal to u1, y1 prime plus all the way up through un, yn prime, using the fact that we are assuming that u1 prime y1 plus un prime yn is equal to 0. Similarly, we wind up getting that the kth derivative of y is equal to u1 times y1 kth derivative plus all the way through un times the kth derivative of y sub n. And this will hold as long as that u1 prime times y1, the k minus first derivative of y1 equals 0. So this will hold for this will hold for 0 less than or equal to k less than or equal to n minus 1. Again, basically at each stage when we go to do the product rule, we would go u1 prime times the kth derivative plus u1 times the k plus first derivative. And so the part where the u1 prime times k will, or times the kth derivative will all just go to 0 as long as it falls in our set of n minus 1 equations we started with. So we know all of the derivatives up to the n minus first derivative. So we get then that our nth derivative should just be u1 prime times the n minus first derivative of y plus u1 times the nth derivative of y plus all the way up through un prime times the n minus first derivative plus un times the, yes, I just missed an n. So un prime times y sub n, n minus first derivative, plus un times the nth derivative of yn. I realized I missed the ones on my y1s in that first component as well. Let me just update my screen quickly. Again, I'm just performing product rule on each of the terms of the equation for the n minus first derivative. So we would have had the n minus first derivative would have just been u1 n minus first derivative of y1 plus all the way up through un n minus first derivative of yn by that previous rule, performing product rule on that, we would get u1 prime times the n minus first derivative of y1 plus u1 times the nth derivative of y1 all the way down to un prime times the n minus first derivative of yn plus un times the nth derivative of yn. So plugging these into our differential equation, so plugging these into p0 of x times the nth derivative of y plus all the way down to pn of x times y equaling capital F of x. We will have p0 of x times u1 prime y1 n minus first derivative plus, I'm going to rearrange these all the way up through plus un prime times the n minus first derivative of yn, and then plus u1 times the nth derivative of y1 plus all the way down to un times the nth derivative of yn. That's all just multiplying p0 of x. Then we'll add plus p1 of x times, again, all of our other derivatives. We are looking at just u1 times that derivative of y1 all the way up through un. So we'll have u1 times the n minus first derivative of y1 plus all the way down to un times the n minus first derivative of yn. Then we'll keep going. I'm going to shift all of this to the next page so I don't have an equation just split in the middle. So that was our p1 times, then we'll go all the way down to pn of x times u1 y1 plus all the way down to plus un yn. And this is all equal to f of x. I apologize, I need to update my screen. All right, so we had our pnx times u1 y1 plus all the way up to un yn, and this should all be equal to f of x. So if I rearrange this, we have p0 of x times u1 prime n minus first derivative of y1 plus all the way through un prime times the n minus first derivative of yn. That's the only component that has ui primes. Then we will have plus p0 of x times u1 y1 nth derivative plus all the way down to un yn or yn nth derivative plus all the way up through pn of x times u1 y1 plus all the way up through un yn. And then again, this is all equal to f of x. Now note that this component, the p0 of x times all of the stuff that did not have the ui primes, that was just ui times the derivative of yi, that is just a combination of homogeneous solutions plugged into our left-hand side. This is actually just equal to 0 since the yi are all solutions to P0 of x times the nth derivative of y plus all the way down to Pn of x times y equaling 0, the homogeneous equation. So we wind up just getting that the original differential equation simplifies to P0 of x times u1 prime times the nth derivative, the n minus first derivative of y1 plus all the way down to un prime times the n minus first derivative of yn equal to f of x. And so we get u1 prime times the n minus first derivative of y1 plus all the way up to un prime times the n minus first derivative of yn is simply equal to f of x over P0 of x. Then what we get is we get a system of n equations and ui prime. So then we have the system. I'm going to write it using matrices. So we have the system y1, y2, all the way up through yn as our first row, y1 prime, y2 prime, all the way up through yn prime as our second row. Then the n minus first derivative of y1, n minus first derivative of y2, all the way up through the n minus first derivative of yn as our last row. This matrix multiplied by the vector u1 prime, u2 prime, all the way through un prime should be equal to all of those equations until the very last equation, that yi or ui prime times yi to the k minus first derivative, adding all those up, was equal to 0 until the very last one, which we just found was f of x divided by P0 of x. We have a system that we can work with. This particular system lends itself really well to Cramer's rule because we do have the answer vector, or the vector that we're trying to equal is primarily zeros. It just has one term. So we can use Cramer's rule to solve this. So we will use Cramer's rule to solve. Cramer's rule says that if we set, so again, if W is the determinant of our matrix we just had, so y1 through yn, all the way down to y1 n minus first derivative, up through yn n minus first derivative. So W is this determinant. And this is just the Wronskian. And if we set Wj star, I'm just going to put the star over Wj. This is my own notation. This is that same matrix where we swap out the jth column with our answer vector. So y1 through y1 and minus first derivative, and we're going to swap out that jth column with that vector that's all zeros except the last row was f of x over p0 of x. And then we have our yn through the n minus first derivative of yn on the right hand side. So again, this is swapping out the jth column for our target solution, the zero vector with f of x over p0 as the last, very last entry. Then what we get is that uj prime is equal to wj over wj star. Now, if we set wj to be the subdeterminant of the original matrix, removing the jth column and the last row, then we get so we wind up getting, due to the fact that that jth not column is now all zero except the last row, we get that our wj star is simply equal to the part of the determinant based off of that f of x over p naught of x in the jth column and last row. So we'll use the jth column as our part for the determinant. The position we're in there is negative, we'll have the nth row and jth column. We'll have a -1 to the n plus j. And then we'll have times f of x over p naught of x times wj. So what we wind up getting is then our u j prime is equal to -1 to the n plus j times f of x over p naught of x times wj divided by w. So in order to solve for those ui primes, we just need our Wronskian matrix, the matrix for calculating the Wronskian, and we need to know the subdeterminants where we eliminate the last row and last column. So in order to find our u sub j primes. We just need to know f of x, p0 of x, and our Wronskian and the subdeterminant of w, or wj, eliminating the last row in column, sorry, the last row in column j. So you do not have to work through any of this background information at all. You are welcome to jump straight to our equation for each of our uj primes and just solve from there. So we'll be working with matrices, finding determinants, finding subdeterminants, but you don't need to do all that mess I did to derive this equation. In the next video, we'll do a couple, well, in the next two videos, we'll do a couple examples where we actually solve this, solve the equation.